Okay, this is the second hour of Physics 1B for November 16th. We're going to continue solving this problem, doing B, C, and D, and then we're going to move on to talking about entropy. So in this problem, we're analyzing a Carnot engine. We want to find the part B. We want to find Q, W, and delta U for each step for the entire cycle. Okay, so I almost feel like we have to kind of start a new page here. I can't solve the rest of the problem here. So maybe here. We know what we need to do. So maybe we just go down and then move this picture so we can kind of, I don't know what to do. There's not a lot of room to do this. All right, let's just see what we can do if we just kind of slowly expand our workspace here. All right, part B. We want to find Q, W, and delta U for each cycle. So maybe it would make sense to start with the ones for which there's isothermal expansion and isothermal compression. Because what would delta U be for those steps? For like 1 and 3.
For the isothermal, you said?
Yeah, what would delta U be?
It should be 0.
Yeah, that's right. So for the isothermal steps, we know that delta U is equal to 0, and we know that Q is equal to W, basically. Okay, and then how could we find what Q... So we know Q is equal to W in this case. So for example, this is B for A to B, for example. That QH would be equal to W. How could we find what that would be equal to? What would QH be, or what would the work done be in that case?
I'm sorry, what did you say one more time? I couldn't quite hear.
So I'll repeat the question. I would like someone other than Cam to answer because he's been answering all the questions, and it gets kind of annoying only having one person answer everything. So in this process, the isothermal process, for we're trying to figure out what the work that's done is. How could we do that? Can someone else answer? You can answer in the chat, or you can vocally answer if you want to. How can we find the work done? What did we do here? I left my water in the other room. I'll be right back. We can use Q equal to W, but we don't know Q, and we don't know W, right? So we got to do something to calculate them. You can look at what's right there. I'll be right back. Yeah, that's right. What John said is correct. We can do the nRT equal to natural log of, is it P or PB? I thought it was the volumes. It's this basically, right? We can just copy that and pull it down. Because we have all the variables here. So let's do that. Oh, you can do the volumes and the pressures as well? Sure, right, because, yeah, it's isothermal, so we have this too, right? Yeah, good point. Yeah, good point. We know that the pressures and the volumes are related to each other as well. That's right. Okay. I want to let me click away from that. Maybe if I start writing, it'll go away. Yeah, well, okay. All right, so... Uh-oh, I got this problem where it's doing this thing again. Here we go. All right, so if we erase this... this is going to be, I think VB is double VA. So this is going to be the log of 2. So we'll have nRT, which is 0.2 mole times R, which is 8.31. And then times TH, which is 500. And then the log of 2. So that will give us the work and QH as well. So I got 576. It's going to be in joules. We can do the same thing for the other isothermal process, which is from C to D. We know that QC here is going to be equal to the work done, and the work is going to be equal to, similar to the previous one, will be NR times TH, and then it's the natural log of its final over initial, right? So it's going to be VD over VC. This should give us a negative quantity when we plug everything in. So we get QC is equal to W is equal to, again, 0.2. Okay, TH was the wrong one here because this is the cold part of the cycle. So this should be TC. This is times 300. And then a natural log of VD is this one. And VC is this one. So that gives us QC, which is equal to W, is equal to and let me know if you guys get different answers to what I'm putting here. So I got negative 345. I guess I'll not round it. So this is going to be negative 344.8 joules. Okay, I'll just give it a second. Let me know if y'all get anything different. And I guess we can also just check the book here because it's such a long problem. I don't want to. Okay, 576 and negative 346. Is that what we got? Yep. It looks like it's off a little bit because they're doing some kind of rounding. I guess I rounded 2 technically here, and I rounded here. I could probably have avoided that, but I don't want to redo those calculations just to get this number to be slightly different. So roughly those are correct. And now we need to do the other portions. Now we got to find QW and delta U for the 2 adiabatic processes. For these, we know Q is equal to 0, as it indicates on the diagram, because adiabatic means that there's no heat exchange with the environment. So given that Q is 0, and then going back to our the first law states that delta U is equal to Q minus W. So that means that the change in internal energy should be equal to basically negative W. This is going to be for the adiabatic processes. So as long as we can find W or delta U, that works just fine. What do y'all think? What would be the easier one to calculate here? The work or the change in internal energy? Which one do we do based on the information we have here? The work, how would we find the work, Andrew? So the adiabatic portions are this one and this one. I wonder if we could have done these other two parts that we just did here by doing it's not constant volume and it's not constant pressure. Never mind. Isn't U easier? Sure, Baron. Why would U be easier? What can we do for U? NC delta T, right? You're saying to do NC delta T. You're fine, dude. Okay, now there's so many equations in this particular course. I feel like this is the Q, isn't it? Is that what you're thinking of? Isn't this the heat exchange at constant volume or constant? Is this really delta U? Maybe it is. I don't remember. I literally have to go back to the notes or the textbook, which I don't really have anything other than this electronic copy. What do y'all think? Okay, here we go. So Kenny's grabbing an equation from Baron's correct, but I can't really tell what he's trying to say here. Like, is it this equation then, John? Is that the right equation? Okay. So we know it's not a constant volume process to go from B to C. We also know it's not a constant pressure process, right? The pressure's changing from B to C. The volume's changing from B to C. So what do we use for C then? Like what will we use here? Is this that thing where even though the volume is changing, the value of U is always equal to this regardless? Is that how it works? Sure, we can use the relation of CV to gamma for sure. But what I guess what I'm asking is just to kind of remind the theory and stuff, because I'm clearly not very straight on this. I remember when we were talking about adiabatic processes that we said something. I mean, this is how we eventually got to the idea of what gamma is, I believe, was that we said something like, for an ideal gas, the internal energy only depends on the temperature. And then we said something about how when you deal with a constant volume process, the work is zero. So delta U ends up being equal to Q, so that this quantity basically can always be used to find the change in internal energy. Does that sound right? What I just said? Like, I'm gonna go way back to our notes here and see if I can't find which day we did this. We said, I mean, here's an example of where we're using it. This is not a constant volume process, but there was a constant volume portion of it though. And then this is the equation. We can definitely use this. This is the equation that Kenny gave us, right? During an adiabatic process, the work done is equal to this. And the work done is equal... Yeah, here we go. Yeah, we can do this. Work done on or by the system is equal to N times CV times delta T. Yeah. And that was true because, like, if we go back to the theory, I think this is the theory portion. Yeah. Q is 0, so delta U is equal to negative W. So we get this expression, but then we basically just, anytime we see a du, we basically just write this, even if it's not a constant volume process. Okay. All right, I'm on board then. I think we can do this. I think that's right. That looks right to me. All right. So let's go. So what do we have now? We're wanting to find delta U for the adiabatic process, which is from B to C. So let's do B to C first. We're going to say delta U is going to be equal to number of moles times the molar specific heat at constant volume times the change in temperature. So for this case, that's going to be 0.2. Now for CV, we have to use gamma as John was saying, John said. So that was that. Let's see if I can remember this. Something like gamma is equal to, I think it's CP over R, where CP is equal to CV plus R. Am I doing this right, or is it CV over R? I think this is correct, because I don't remember there being... Well...
Did you say the gamma?
Yeah, gamma is CP over CV. That's right.
That's right. CP over CV.
Okay. So this is CV in the denominator. Thank you. And this allows us to figure out what CV is. Yep, like this. So we get 1... Okay. Let's just continue this down here. We'll put this right here. So if gamma equals CV plus R divided by CV, it's also equal to 1 plus R over CV. So gamma minus 1 is equal to R over CV, which leads to CV is equal to R divided by gamma minus 1. So it's equal to 8.31 times 10 to the negative... Nope. Joules per mole Kelvin divided by gamma minus 1, which will be 0.4. We're going to be using CV a bunch, so we might as well calculate it. All right, so that's our value for R. It has units, or for CV, that's joules per mole Kelvin. So then, coming back over here, we'll say that delta U is going to be equal to 0.2 moles times CV delta T will be TC minus TB. So TC was... Oh, well, it's T, basically just T cold minus T hot, right? Yeah. Okay, we should get a negative number here. This was 300 Kelvin minus 500 Kelvin. So I get negative 831. That's internal energy, which is going to have units of joules. So that's B to C. See, now the work's supposed to be greater than 0 now, though, for that part. Oh, right, because the work is the negative of the change of potential energy. So then the work is just the positive of that, plus 831. Okay, that makes sense. All right. So then if we want to do the other process, which would be from D to A, I believe, right here. So for D to A, there's only one thing that's going to change, right? The TH and TC are just going to switch places. Is that correct? So for this, I think what we're going to get is delta U is positive and the work is negative. Does that seem right? I guess we can check, but I just want to know if it all makes sense, like, logically to you guys before we check. The only thing it's going to be is that, like, the final temperature is going to be greater than the initial temperature now. So does that look all right to everybody? Anyone have any questions? Yeah. There's 832, but it's the same thing. Okay. All right, that was part B. Q, W, and delta U for each step. All right, now we want to basically find the efficiency directly from the results of part B, which is what we just did, and compare with the value of doing that equation. All right, let's do that part first. So the efficiency according to the equation that we derived. All right, so this is the last part. Efficiency is equal to 1 minus TC was the numerator and then TH in the denominator. So this is 1 minus 300 divided by 500. So 1 minus 3 over 5 is 2 over 5, so this should be 0.4. The other way to calculate the efficiency would be to use, what is it? Find the efficiency directly from the results of B. B was to find QW and delta U. Okay, so there's our Q, and then our delta U is down here. What do we want? We want the net work done or something like that? Is that how we would do this? We would do the net work done by the system, which would be basically this minus this, and then divide by QH, so that we could use, like, the equation here. It's basically the same thing, right? I mean, it's the same problem, it's just now we just need to... Okay. So... just thinking for a second. I think that's right. So in one cycle, yeah, entire cycle we're talking about. Oh, that's the piece I didn't do. I see now. Okay, well, that makes a lot more sense when I read it like that. And the entire cycle. Okay, so if we want to do QW and delta U for the entire cycle, delta U for the whole cycle... delta U is 0, right? Because delta U is 0 for these 2 points, and delta U is net 0 between these two. For the work is going to be 576 joules minus 344.8 joules. So 576... so I get 231. We call this like the network. And that's it. Then we just need to use QH. So 231 divided by 576. You also get 0.4. Which is good. It's the same thing. Well, this is a long problem. And it's pretty tricky, too, because you got to really think about, like, which part is adiabatic, which part's isothermal, and then which equations apply to those. Got to be kind of careful. Okay. Anyone have any questions? Oops. Yeah. Sure, Baron, no problem. All right, so let's go through kind of like what we did. Let's take this whole thing through. So we were given a bunch of information about our Carnot engine. And we had hot temperature, a cold temperature, a number of moles. We were given one of the state variables, which was the pressure, as well as, I think we got the volume too, right? Nope, we didn't get the volume, but we could calculate it immediately here. And then what we said is, okay, we need to like think about each of these points. For the isothermal process from A to B, we used that equation. This is the one I made a mistake on first. And then we calculate the pressure at point B. Once we have the pressure at point B, actually as a separate calculation, we could use the adiabatic process to find the volume at point C. We did that here. I also made a mistake here when I raised my power thing. I didn't do that properly. So we raised it to the power of 1 over gamma minus 1, and we solved this one. We got the volume at point C. We used the volume at point C to use the ideal gas law to find the pressure at point C. And then we came over here and we found the volume at point D by using another adiabatic process, D to A. Got that. And then we found the pressure at point D once we knew that, using the ideal gas law. We used all that information, well, some of it, I guess. So we used the ratio of the volumes to find the work done in the isothermal process. Then same thing right here for the other isothermal process. And then for the adiabatic processes, we had to say delta U is equal to N times CV delta T, even though it's not a constant volume process. We know for an ideal gas that the internal energy is only a function of the temperature. So whatever quantity you get from this, even if it's not happening during a constant volume process, has to be the same thing as what the change in internal energy is. So knowing the difference in temperatures, that was very easy to do once we understood how to do it at least. Yeah, so I think overall it's just important to kind of know in these problems like which part's isothermal and which part's adiabatic so that you can use the proper equations. The adiabatic ones are the ones where these gammas show up. Isothermal ones just have the normal kind of pressure-volume relationships that you may be familiar with from your chemistry class. This is what I remember learning long ago in chemistry. And then understanding kind of, you know, none of these equations are difficult. What seems to be very difficult about 1B, at least in these processes, is knowing which equation to use at which time. Even though individually none of the equations are that hard. We didn't have to do any calculus. Everything we did was algebra. It can still be quite tricky to keep track of when you can use which equation. So I guess that's the biggest point. All right, did you see what I fixed, Baron? Is that good now? All right. Okay, so let us move on to talking about something else. The rest of the class will be, we're going to talk about entropy. So let's do that. If I can get through most of what I want to talk about, I'm going to try to show you guys a video from PBS FaceTime on entropy that's really good. And will probably help you visualize it better than I can do just on this little whiteboard. All right, so entropy is, I mean, we'll just put it, I'll tell you straight up what it is, and we'll kind of go through the math of it as well. So entropy, I'll just say this, I don't know if it's going to mean anything to you. It's a measure of randomness. And what it does is it allows us to, because we can measure randomness, and I'll talk about how we do that, it provides basically a way of quantifying the second law of thermodynamics. I'll just say second law. Hopefully you know that I mean of thermodynamics. Just to remind you what that is. There we go. So there's multiple statements of this, but one statement is, it is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts heat completely into mechanical work, with the system ending in the same state in which it began. That's a really complicated way of saying it. Another way to say it is this one. It is impossible for any process to have as its sole result the transfer of heat from a cooler body to a hotter body. You could say this means that, things naturally do not flow from cooler bodies to hot bodies. Like, heat does not flow from cooler bodies to hot bodies. Okay? And part of the reason why we said this happens is because if you think about the idea of a body sliding to rest due to friction on a table, it's organized motion that gets converted into random motion, and it's very easy to convert organized motion into random motion, but you can't do the reverse. Not completely, at least. Okay? All right, so that's the second law of thermodynamics. And in order to measure exactly how that works, in order to kind of quantify how that process works, we introduce entropy, a measurement of kind of randomness. All right. So to understand this from kind of a macroscopic perspective, we consider the following scenario. So we take some kind of gas and we add a heat dq to it. And then we let it expand, but we keep the temperature constant. If we keep the temperature constant, and this is going to be, as usual, this is going to be an ideal gas that we're going to talk about. We're going to describe how this works for an ideal gas and then kind of expand it to all gases. So we add heat dq to an ideal gas. We let it expand at a constant temperature. If it's done at a constant temperature, what does that mean about the change in internal energy? Ruja said in the chat, so nothing naturally heats up on its own. Yeah, that's right. That's right. You can't have, like, you're sitting in your room, right? Let's think about it this way. You're sitting in your room right now, or you're sitting somewhere, or you're standing, or whatever you're doing, and your body is in thermal equilibrium with your environment, right? If the temperature in the room is colder than the temperature of your skin, you're going to feel cold, right? So if it's 50 degrees in your house, you're going to feel cold. If it's 80 degrees in your house, you're going to feel warm, right? But your body comes into kind of a thermal equilibrium with the environment. Now let's imagine you're out hiking in the mountains and it's snowing and it's cold outside, right? And you think, how could I heat myself up? Well, you could do things like rub your hands together, but that's only so it's not going to be very good in general. Just rubbing your hands together will get you a little bit warm, but it won't warm your entire body up, right? So then you think about physics and you think, oh, you know what I learned in my physics class? I learned that temperature is really just fast motion, right? It means that the molecules on average have, when you have a high temperature, they have a lot of kinetic energy. And so you think, well, what if I could just take all the fast-moving molecules around me? Because even though it's cold outside, certainly some of the molecules in the air are moving really quickly, and some of the molecules in the air are moving really slowly, right? So what if I could just basically harness all the fast-moving molecules and kind of use it as a way to heat myself up, right? That's kind of what you're saying, Ruja. And the answer is that's impossible. It would never happen, although there is some very low probability for it to happen. It could happen, but it would never happen in any realistic sense, just like you'll never win the lottery, that all of a sudden only the hot molecules are moving towards you and that they just kind of suddenly warm you up, right? That would never happen. Does everybody agree with that? Because you're surrounded by warm molecules and cold molecules. There's kind of a statistical distribution of them. Some of them are hot, some of them are cold. And you're hit by the same number of hot molecules as you are cold molecules. And so it just averages out. And that's where the idea of thermal equilibrium comes from, right? So the second law basically says that there's no way to just kind of like only harness the ones you want, because there's just too much randomness going on. There's just too many of them, basically, as we'll see. All right, so we add a heat dq to an ideal gas, right? We let it expand at a constant temperature. So I'm just going to ask again, what does that mean that the change in internal energy is going to be for the ideal gas if we do it at constant temperature? 0. Yep. So that tells us that the amount of heat that we add, and we're saying it's some kind of small infinitesimal amount of heat, is going to be then equal to the work that's done by the gas, right? So if the gas, for example, is in, if our gas is in a, just the standard thing we normally do here, we got a gas, we add dq to it. The piston moves up, so it does some work dW on its environment, right? Okay, heat in, gas does work, right? Okay. So what we know then, and we've done this many times before, that if dq is equal to dW, and dW is equal to PdV, and PdV is equal to nRT, we use the ideal gas law, as we normally do, nRT divided by the volume times dV. We did this at the beginning of the section on the Carnot engine. Then we get this relationship that dV over V, okay, the amount by which the volume expands, and what's that going to be? Well, the idea is that the container will move up a little bit, so it's going to increase in its volume by some amount, divided by the total volume, should be equal to what's going to be on the right-hand side now. So we're basically going to take the t and we're going to divide it over to the left right here. In fact, this might be a little more clear if I actually do one more step here. So I just say this is equal to dq. Then we can relate it by dividing the t to the right-hand side and the nr. We get dv over v is equal to dq over t and then times 1 over nr. All right. So we think about what's happened with our gas, and we'd say that because the gas has expanded into a new volume, a larger volume, that the molecules are now moving in this larger volume and have more randomness of position, right? So when we think about this quantity right here, dV over V, so the molecules are now moving in a larger volume, as I said. And basically have more randomness to their position. Right, so what do we mean by randomness of their positions? Well, if we consider that an object moves from some volume, so we've got gas molecules here, some volume V, and you expand to a bigger volume, so now the molecules occupy more space. When I say randomness of position, what I could do to kind of clarify what I mean by that is I could cut this box in half, okay? And we could say that it went from volume V to a volume 2V, let's say, right? Now, before we expanded the size of the box, right, in the first case right here, in case 1, the odds of finding a molecule in the lower half of the box, basically the odds of, in the first state, the odds of finding a molecule in this space right here would be 100%. That's kind of a stupid thing to say, but I think it's necessary to say it. Would you agree? If I say that all of the molecules are occupied by this volume V, the odds of finding one of the molecules in that area is 100%, right? But when I expand it to the new volume, right, and I say, okay, well, now the molecules can move into a volume that's double the size, the odds of finding a molecule in the lower half of the box is probably 50% now, right? So while the molecules were more localized in this case, they also had less randomness because they just flat out have less space they can occupy, right? This is like, to compare it to dice, this would be like the difference between rolling a 10-sided die versus a 20-sided die, kind of, in a way. It's actually even more, but for the purposes of an example, I think this kind of makes sense, right? A 10-sided die, there's basically 10 options of what you can get as a result. A 20-sided die, there's 20 options. So the 20-sided die is going to have basically more randomness associated with it, right? So a gas that's confined to a volume V compared to a gas that's confined to a volume 2V, well, there's more randomness in the 2V case because there's more randomness to their positions. There's more positions that these gas molecules can occupy at this point, right? Now, technically, if you get really, really mathematical about it, in both cases, there's basically an infinite number of positions that the molecules can take up within the space, right? Do you guys agree with that statement? That regardless of the size of the box, you might say, well, there's an infinite number of spots that these molecules can occupy, right? So what does it matter, infinity versus infinity? Well, you might just say that this second infinity is twice as big, but mathematicians wouldn't like that. Instead, what you can say is, let's not make it so incredibly mathematical, and let's say, suppose that we break up the system, the box, into grids, right? And we say that the size of our grid is like an angstrom or like a nanometer on each side, right? So you break it up into a bunch of, just like a grid, right? And now you say, okay, molecules can be here, or they can be here, or they can be here, or they can be here. They can be in any one of these little grid spots that we've made. But certainly, when we double the size of the box, we've doubled the number of grid spots, thereby increasing, where the molecules can be, and thereby increasing randomness. I kind of over-explained that, but trying to give you an idea of what entropy is. So that's kind of the idea. More randomness. You have any questions or comments about that? Did someone say something in the homework channel that I need to look at? Oh, I see some of you were answering the questions. Okay. All right, so dV over V, right? This basically then is a measurement of the randomness, right? So dV over V then is a measure of the randomness. And that's what we're looking for. Entropy is a measure of randomness. Because if the change in volume is large, then you're going to get a large amount of randomness. However, that's dependent on how much volume you had to work with to begin. So if we double the volume, you massively increase the randomness, right? Because the change in volume is, 100%, right? If instead you have a volume that goes from, let's say, 9 liters to 10 liters, well, then you've only changed by 1, right? So your randomness would be basically 1 over 10. That would be your increase in randomness. 1 over 10, right? So that's why the volume shows in the denominator. If you already start off with a big volume, like if you go from 90 to let's say 99. No, that's a bad one too. No. We want to go to like a big volume. So let's say you go from 900 only up to like 901. Well, now you've got increased randomness of only 1 over 901, right? So this is a lot less of an increase in randomness because you barely changed the size of your container from 900 liters to 901 liters, right? Does that make sense? So the actual volume also matters, right? The change is important, how much of a change you get, but the change is always going to be relative to the volume itself. So if you start with a smaller volume, then you're going to get more randomness compared to a larger volume where you get less randomness. All right? So that's a measurement of the randomness, the amount by which you increase the volume in this system. Now, that would be a decent definition of what randomness is, except that it's not always the case in a system involving, gases or whatever, that the volume changes. We do a lot of systems where the volume doesn't change. And even if the volume doesn't change, things like pressure or heat can come into the system, and that can increase randomness as well by increasing kind of the velocity of the molecules. So we notice from this equation here that dV over V is also proportional to, so we'll use this proportionality symbol that we love to use in physics, is also proportional to dq over t. Right? Yes, there's this 1 over nr that shows up in here, but what we do is we basically say this is going to be our definition of what entropy is. Okay? And in particular, we're going to say that the entropy, we're going to use the symbol S, so S is entropy, capital S. There was a time when I knew why S was entropy. Maybe some of you know. Does anyone know why we use S for entropy? It's really something we can go look up. All right. Other books probably use different things too. I can remember books that didn't use S for entropy, so. Anyway, so what we do is we basically define entropy to be equal to, so we use the triple line here to represent this as definition. We're going to define entropy to be dq over t. This is going to be only relative to infinitesimal processes. So this is only going to work when the amount of heat that we add to the system is a small amount of heat. So this is only going to work for infinitesimal changes in Q or whatever. What we're going to call an infinitesimal process. We can, of course, take an infinitesimal process and another infinitesimal process and another one, and we can basically add them all together until we get a finite process. All right? So, what does this represent? Okay, so now what we can do as well is, it's not just infinitesimal, it's an infinitesimal reversible process. I'm sorry. Infinitesimal reversible process. I hear Baron put an explanation in the chat that I'll read here in a second. Infinitesimal reversible process. Not reversibly. What? I've got this selected. Oh, I had like 2 things selected. All right. Infinitesimal reversible process. Okay, so let's see what Baron said here. He said, it is generally believed that Rudolf Clausius chose the symbol S to denote entropy in honor of the French physicist Nicolas Sadi-Carnot. His 1824 research paper was studied by Clausius over many years. Oh, okay. That's cool. All right. Good to know. All right, so this is going to be for an infinitesimal reversible process. And if you have a totally reversible process, I think you can say that this would be one in which every step was reversible. Then you could say that delta S ends up being equal to just Q over T. Okay? So that the change in entropy of the system is a function of temperature and a function of heat. Okay? So let's see if this makes sense. Say I have a system and I add heat to it. Okay? Does it make sense that the entropy should increase? Will the system become more random just by adding heat to it? Yes. Why is that? Why would the system become more random just by adding heat to it? Greater movement of molecules? Yeah. So they're going to be... Yeah. Okay. That's right. So why is the temperature in the denominator then? It's certainly the case that if things are hot, they've got a lot of randomness, right? And then by adding temperature, by adding heat to the system, right? Then, that's going to basically increase the randomness, right? So why is the T in the denominator? So the T in the denominator is basically similar to the reason why the volume is the denominator here. If a system is already really hot, let's say you have a system that's at 1,000 Kelvin, and to that system I add 100 joules of heat, it's not going to have a huge change on the system, right? Whereas if I have a system that's at a very cold temperature, like 50 kelvins, and I add the same amount of heat, there's going to be a bigger change overall in the overall randomness of the system, right? That's why the temperature is the denominator, is because if it's already hot, then adding heat to it isn't going to significantly increase the randomness, right? But if it's really cold, like let's say, for example, you're talking about a piece of ice, and a piece of ice basically, let's say, melts because you add heat to it, well, you went from this ice system that was highly ordered, a solid, much more ordered than a liquid, right? And by adding heat to it, you made it melt. Well, then there's going to be a big increase in entropy in that process, right? Okay, so we can only really use this equation if we have a totally reversible process. Yeah. But in general, we can say that any reversible process can be broken down into infinitesimal steps. And we can say basically then that our delta S can be defined as being the integral of dq over dt, or dq over t, sorry. So that's going to be the main way we're going to calculate entropy, is by integrating dq over dt, or dq over t. Change in entropy is always going to be independent of path, and the entropy is going to have a definite value for each state. And we can apply this same equation to an irreversible process as long as we invent a path between the two states that is reversible. So I'm going to go through that again. I don't know if I want to write all this stuff down. Some of it I want to write down, though. Okay, so one thing we can say is that entropy is independent of path. For a given system, the value of the entropy has to be kind of fixed. It doesn't. The way you can think about this is it doesn't matter how the system got to that state. A measure of how much randomness there is should be independent of how it got there, right? It should just be really a measurement of the state itself, which means entropy is actually another state variable now, if you think about it, right? What are our state variables in Physics 1b? They're the big macroscopic things that we use to talk about gases and systems, which are pressure, volume, and temperature, right? Entropy is now another state variable, basically. I guess another one would be internal energy is another state variable, right? So U, S, P, V, T are our state variables. Okay. Q is not a state variable because we're always adding heat or extracting heat from a system, right? So entropy is independent of path. It only depends on, it has a definite value for each state. And we can calculate an entropy change for an irreversible process by breaking it up or changing it to a process between the path between the two states that is reversible. So for an irreversible process, which is basically almost all real processes, right? We can find the entropy by inventing a path. You find the change in entropy by inventing a path So for an irreversible process, what you have to do is you have to come up with a reversible path between the states. And in doing so, you can use it to figure out what the change in entropy is going to be for that process. All right. We can state a couple things. I don't know if we want to immediately do a problem or if I want to make these statements. There's a lot of statements that I have written down here, and I think that we want to do problems first, but I'm going to kind of hint at a few things here. Adiabatic expansion, right? In an adiabatic expansion, what would the entropy change be? Can you figure that out? Look at this equation. Think about adiabatic, what it means. What would the entropy change be for an adiabatic process? 0.
I believe not.
0 is right, Kenny. That's right. Because dq is 0, right? You don't add any you don't add any energy to the system in an adiabatic process, so the entropy change is 0. That's right. So for a Carnot cycle, the total entropy change is 0 for a full cycle, and pretty much any reversible cyclical process, if you can get back to the same initial state, then the entropy change is going to be 0. Doesn't mean that you don't have entropy changes within the system, but for any reversible cyclic process, the entropy change is going to be 0 for the full cycle. I mean, we just did this problem related to the Carnot engine, and the idea would be that because every single process is reversible, and you end up back in the same initial state, and entropy is independent of path and depends on just kind of the state. So if you get back to the same state at the beginning, and you do so without losing any energy, then it's going to have to be no entropy change. Any irreversible process automatically increases entropy. And one thing we can say, we're going to go on break here in a second, but in general, we can basically rewrite the second law of thermodynamics using entropy as a definition. This is the simplest way you can state the second law. When you take into account all systems, entropy always increases or remains constant. I don't know if I need to say this part, but I might as well. There is no way, all right, there's no way in which entropy can decrease when you take into account everything that's going on, all right? There's a couple pictures here. I probably should have pulled these up right at the beginning, just to kind of show you something in general about entropy. And we'll come back and we'll do some problems and stuff. We're going to read this when we come back to you. All right, bunch of questions about entropy. There's like 4 or 5, but here's these 2. This one I'm going to grab for now.
Oh, I have a question, Professor.
Yeah, go ahead, please.
So, if I'm understanding right, the cold reservoir in the Carnot cycle would be 0 for the temperature?
The temperature 0?
Is that, or, well, because what I'm trying to understand is that the change in entropy is 0, right?
For the whole process.
For the whole process.
Not for any one step, the entropy change. So, okay, so for 2 and 4, the entropy change is 0. But for 1 and 3, the entropy change is not 0. In one case, it's going to be positive. In one case, it's going to be negative.
Okay. I was thinking, is there a 0 change in entropy, but the efficiency is not 100% or whatever.
Right. It's not because the temperature is 0. That's not what's going on there, no. All right, so when all systems are taken into account, entropy either increases or remains constant in all physical processes. What this means is that over time, the entropy of the entire system, you could talk about the entropy of the Earth, you could talk about the entropy of the solar system, you could talk about the entropy of the universe if you want to. And in general, what this is saying is that entropy is always increasing. Entropy is always increasing in all processes. And it's a measurement of randomness, which means that things tend to become more random. Okay, this is a good place to stop. We'll start again at 12:20.